Today we're going to explore E. You'll definitely want to take some notes. A graphing calculator might be helpful, and of course a writing utensil. Let's go back to when we first learned about pi. Remember, what does pi represent? It's circumference divided by diameter. We also talk about how it is an irrational number. It goes on forever. But even though the value is irrational, we can still simplify expressions that contain pi. It's almost as if we treat it like a variable for the time being. For example, if this was an x, I would treat it the same way. We would distribute our exponent to both values. Or here, we would reduce our fraction, take care of our exponents, and then simplify any other exponential rules that we need to take care of. Today, we're going to explore Euler's number. Euler's number is approximately 2.71828. This is also an irrational value, just like pi, and so we're going to treat it very similar to pi. Make note of the approximation symbol. We're going to use that a lot in this section. E is one of the most powerful mathematical numbers to go along with I, imaginary numbers, which we've worked with, and of course pi. Where does E come from? E comes from the exponential growth formula. If we take a look at all of these examples, if we were to compound interest twice a year, each day for 1 year, each minute for a year, each hour for a year, all the way to infinity, we would always approximate 2.718, or E. Let's explore how to simplify the expression. Again, treat E as you would pi or any other variable. We want to follow the same rules. So to start off, I have 2 times 6, which would give me 12. I have E, and these two exponents, since I'm multiplying the bases, I would add them together. So I would end up with E squared. Another example is exploring the division rules. Follow those same rules. 24 divided by 4 would give me 6. E to the 8th divided by e to the 5th, I would subtract and end up with e to the 3rd. Now we can take it a step further and we can actually evaluate these by using our calculator. If I plug in 12e squared into my calculator, I end up with approximately 88.67. Again, make sure to use that approximation symbol. 6e to the 3rd gives me approximately 120.51. Let's take a look at a third and final example for simplifying. Whenever we have an exponent on the outside, we need to distribute to every piece. That's been a common rule that's been missed. So 4 to the 3rd and e to the, we need to multiply those exponents. So we end up with 6x. Take it another step and simplify 4 to the 3rd, which would give me 64. And we would leave e to the 6x as that's a variable, so we can't simplify it any further. So what else can we do with the value of e other than simplifying? As we've done for the last few lessons, we can also graph. To graph the natural base for e, we are going to continue using our tables. To start off, we need to first find our parent table. For your parent table for e to the x, you're going to want to stick to those standard values of -2, -1, 0, 1, and 2. To find out what my y value would be, you will definitely need a calculator, and you're going to have to plug in e to the x. If I plug in e to the negative 2, I end up with approximately 0.135. If I plug in e to the negative 1, I get approximately 0.367. E to the 0 follows the same rules. Anything to the 0 power is 1. E to the 1 power is approximately 2.7, and e squared is approximately 7.38. If we go beyond 2 to 3, that's going to be above 20, so we're not going to deal with graphing those higher values. Our parent graph, therefore, is going to look similar to our exponential growth and decay graphs. Since our values are so small on the left side, and they slowly rise off to the right, and then grow quickly as we approach 2 and 3. Just as exponential growth, we're going to have an asymptote, meaning our graph is not going to cross a certain horizontal line. So let's answer these few questions. Growth or decay? If I look at the graph, it's going up to the right, so that would be growth. The asymptote would be the x-axis, or the value y equals 0. That would be a dashed line that my graph is never going to cross. The domain is going to go forever left and forever right. And the range relies on that asymptote. So we're going to go from 0 to infinity. Notice the 0 will have parentheses because it's never exactly 0. Make sure that you jot down this parent table because we're going to reuse that table with our next few functions. Let's take a look at how to graph the following function. We're going to use the same rules for our tables that we've used in the past. The value up front is still your vertical stretch. The value with your x is still your horizontal shift. And your value added or subtracted at the end is still your vertical shift. So let's begin with our parent table. From the previous slide, we know we're going to use those standard values of -2, -1, 0, 1, 2. Using our calculator, we found out what our y values would be, which is approximately 0.135, 0.367, 1, 2.7, and 7.38. Let's apply our rules. Our vertical stretch, we're going to multiply every y value by 2. And our horizontal shift, we're going to subtract 3 from every x value. Remember, it's the opposite sign. If I apply those rules, then I have my new table, which I can graph. So we end up with -5, -4, -3, -2, -1, and decimals that are approximately 0.27, 0.73, 2, 5.4, and 14.8. So let's take a look. If we graph -5.27, -4.73, -3.2 should be exact, -2, 5.4, and -1 is going to be very high up there. So we can't quite get that on our graph. So if we follow that traditional exponential growth model, we can tell that this is a growth as it rises as it goes to the right. The asymptote continues to be y equals 0 because it's not crossing the x-axis. Our domain is forever left, forever right, and our range is between 0 and infinity using those parentheses. Let's take a look at one more example. With the previous examples, and as always, start off with your parent table. -2, -1, 0, 1, 2. If we plug those values in to e to the x, our parent function, 0.135, 0.367, 1, 2.7, and 7.38. Let's take a look at the transformations we're asked to perform. We have a negative in front of the x, which means we're going to take every x value and multiply it by -1. So take every x value and times by -1. We haven't done this very often, but we can see how that rule applies pretty clearly. Next, we have a +1 on the outside, which is our vertical shift. Therefore, it applies vertically to our y values. We're going to add 1 to each of our y values. This creates our new function table, and we have the values of 2, 1, 0, -1, -2. So we can see that our x values, all they did was flip. They changed signs. Our y values increased by 1. So we have 1.135, 1.367, 2, 3.7, and 8.38. If we graph those values, it's going to look a little differently than what we've seen on our previous graphs. 0, 2, -1, 3.7, -2, 8.38. If I follow that general curve, what this does is show me that this is now a decay function, because as I read it left to right, it goes down and to the right. So that -x made a decay function. Our asymptote is related to our vertical shift. Your vertical shift and your asymptote should always be very similar. So we have y equals 1. That would be our dotted line that our graph is never going to pass over. Our domain is still forever left, forever right. But our range is from 1 to infinity, again using parentheses because it's an asymptote, meaning we're not including the value. Even though we are using our tables to find our graphs, you can still use Desmos to see if your graphing looks correct. When you're typing in these expressions, you are going to have to use the A to the B key to end up with your exponent. Your E value, you can use the letter E on your keyboard. Make sure though that I continue to see those tables because those are the values that I'm going to be grading, and I just use the graph to see if you knew how to graph those coordinates correctly. But definitely use Desmos as a way to check your work.